Aloha and welcome to the last talk of ETS 7. For better or worse, always get to wrap up the conference with the last talk, so we're keeping that trend alive today. So my talk today is titled Mirror Mirror. It's about restoring reflective code loading on macOS. So I always like to start my presentations by briefly articulating what I hope you will learn by my talk. So as we can see on the side, hopefully we will learn about all things related to reflective in-memory code execution. And I'll define that more broadly on the next few slides. And talk about why, if you're an offensive adversary, this is a must-have capability that you should be utilizing. And we'll see some challenges of detection. So we'll start with some background and history, talk about approaches that we have to update for macOS 15, and then end with some approaches to detection. So I want to start by talking, or at least thanking and pointing out the fact that there's a lot of previous research on this topic. There's a great article, a Red Canary article. I believe it was written by Brandon. Really great in-depth introductory talk to the topic. Adam Chester recently published some great research, and all the way back in 2015, I was talking about this as well. So what we're going to do is we're going to highlight some of this research and build upon this to show how we need to update it and evolve for macOS 15. So what is reflective or in-memory code loading, code execution? This is my definition, but essentially it's the execution, and this is a keyword, of compiled code directly from memory. And there's two key points here, or several key points. First, we're talking about compiled code. We're not talking about shell code or anything like that. Also, the benefit of this, as we'll see, is that the payload never touches disk, and we'll talk about why this is important. There are some cases where the payload can touch disk if it's fully encrypted, but the unencrypted code never is going to be on the file system. Have some legends of these icons that I'll use throughout the image. The one on the top represents the binary on disk, whereas the other icon is in memory. And the idea is, as we'll see, the attacker generally is going to load something directly into memory on a remote system and then execute it directly from memory. So the payload will never touch the disk. Now, it is important to understand that compiled binaries on disk are very different from how they look in memory. Their layout is totally different. Compiled binaries are optimized for storage. So you can't just take a binary on disk, copy it into memory, and just run it. That would be too easy. So there's definitely a difference in that, and that's an important concept to grasp. Now, you might be wondering why anybody cares about in-memory code loading, especially because we just said there's some challenges and nuances because of on-disk binaries do not look like their in-memory counterparts. And the whole reason I'm giving this talk is because of a decision that Apple has made, which is that no process can read the remote memory of another process. And this includes even notarized security tools. So in this case, Apple has basically prioritized privacy over security. I'm not saying I fault them, but a very unfortunate side effect is exactly this. Process A cannot read the memory of process B. Previously, on older versions of macOS, you could do that. Here's some example code. You would basically open or get a task port to a remote process, and then you could read its memory, for example, scan it for malware. Now, you might also be wondering, well, isn't all code executed from memory? And yeah, that's true. But generally what happens is the binary first exists on disk. The user then double-clicks it, or you launch it from a terminal. And what happens is the loader maps it into memory, and then does a whole bunch of very, very complicated things to get it ready for execution. I've summarized some of these on the slide. First and foremost, it's just reading the file into memory. It then maps other, for example, dependent dylibs, libraries that binary depends on. It applies alignment, memory permission, applies relocation, resolves symbols, executes initializers, does a whole bunch of very complicated things. Now, on macOS, this job is delegated to the loader, whose name is dyld. I actually don't know how to pronounce this. There was a discussion on the Discord channel, and I was like, I thought it was dyld. So I Googled it, and this is a quote from Quinn, the Eskimo, who's kind of like a very well OG at Apple. And as he says, there's various pronunciations. I go with dyld. pronounce it as you want. But the key thing is this is the software component that's built into macOS that does all these complicated loader components. Basically, as we can see, loads the macOS images at runtime and gets them ready for execution. Now, if you are a hacker, if there's nothing else you take away from this presentation, it should be this, that all your payload should be in memory only. And why is this? Well, if we read what's on the slide, there's two main reasons. And the first is that the vast majority, essentially all of detections, are based on files that touch the file system. And so when an adversary drops a binary, all sorts of security tools are going to scan it. That includes Apple's Gatekeeper. It's going to do notarization checks, MRT, XProtect, any third-party antivirus product. And we also have this great quote from Matt Sweesh, basically said that memory scanning capabilities on macOS have always been rather limited, but especially now because of the deprecation of third-party kernel extensions, you basically cannot access memory. And this is what I talked about earlier. Process A, even if it's that is a security tool, cannot read the memory of process B. So let's look at a case study that I think really articulates the power of using in-memory payloads or encrypted payloads that are only decrypted in memory. And yes, this is a Windows case study, but conceptually the same thing applies to macOS. So around 2010, 2011, 2012, there was this very interesting piece of malware called Gauss. And it was uncovered by Kaspersky, and they performed a fairly comprehensive analysis. However, they pointed out that themselves, nor anyone, even till today, so a decade plus, have been able to decrypt the payloads. This is insane. Kaspersky's really good at what they do. And so this is one of the biggest unsolved mysteries in cyber. And the reason they were unable to decrypt the payloads is because even though they existed on disk, there was an in-memory loader component that used an environmental key to decrypt that. And if you couldn't figure out that environmental key, so it was keyed to a specific box, you could not decrypt that. Now, somewhat unrelated, it turns out that the NSA has patents related to key generation for the protection of in-memory payloads. I want to point out that even though these patents are classified, the titles of the patents are not. So, unrelated samples, but I hope this reiterates the fact that advanced adversaries are rather aware and very fond of this capability, especially because it can protect their payloads even once they are detected. So if you're a hacker, you should be using in-memory code execution. If you're a defender, good luck, especially on macOS. So let's now go with a brief history, talking about in-memory code loading on macOS. All kind of started in 2005 with a release of sample code from Apple. The sample code they released is called Memory-Based Bundle. It was uploaded by, again, Quinn, Eskimo 1, and it worked on all versions of macOS 10.3, so pretty old and above. And the reason is that in 10.3, there was this new API that was implemented, which is the ns-create object file image from memory. And we'll see that essentially all the other examples up until macOS 10.15 are utilizing this same API. And we'll talk about more what it does. A few years later, 2009, Mac Hacker's Handbook came out, and it provided a shellcode implementation of code that invoked this same API to directly execute payloads from memory. So this is kind of cool because it's like an in-memory loader. Around the same time, young Patrick was creating Mac malware for, let's just say, offensive cyber espionage capabilities and was utilizing similar approaches. So this specific implant had a self-extracting installer. It would persist a loader module using a zero-day exploit. The loader would then execute with root and would either download or load encrypted payloads and execute them directly from memory. Here's a snapshot of the source code. Nothing super fancy, again, using this same API. About 10 years later, public malware decided to join the party. Welcome. So this screenshot or this table is from the Red Canary report I talked about earlier, and we can see that since 2017 or so, there are now Mac malware samples that utilize this same in-memory code execution approach. So let's briefly look at these. The first sample we have is Apple Juice. If we look at some of the decompilation, they left symbol names in, and their methods are fairly descriptive. They decrypt the payload in memory. They invoke a method, load from memory, which essentially calls memory exec2. And there we can see those same Apple APIs, which support the execution of payloads directly from memory. I blogged about this at the time, but one of the interesting takeaways is like, wait, I've seen this code before. And a few months or maybe a year before, Silence had released some proof of concept code illustrating how to use these Apple APIs to do in-memory code execution. And kind of unsurprising, the malware authors essentially copied this verbatim. We'll see this time and time and again. Mac malware authors often aren't as creative, let's just say, as they could be. Another case study in 2020, we have EvilQuest. This one is also not original. If we actually decrypt various strings within it, we're seeing, A, they're using the same Apple APIs that support in-memory code execution, and also the strings based on the module names actually decrypt to the same strings that Apple used. So EvilQuest malware authors simply used Apple sample code from 2005 to perform their in-memory code execution. Okay, so now let's talk about actually how you accomplish this from a programmatic point of view. And we're going to start by talking about how this used to work really well. We're going to start with Apple's memory-based bundle. And it turns out it's actually super simple because of APIs that Apple previously used to provide that actually performed in-memory code loading for us. So step one, you got to get your payload into memory somehow. Apple's sample code loads it from disk. That's kind of not really what we want to do, right? We want an in-memory payload only. But this could work, right, if the payload was encrypted. You would load the encrypted version into memory, decrypt it, and then execute it. Or if you're a more advanced adversary, you would actually download the payload directly into memory, never write to the file system. Now the magic. Step two, we invoke these NS APIs, for example, the NS create object file for memory and NS link module. These are Apple APIs that perform all the loader magic that dyld does, or did, but does it directly from a memory buffer. This is amazing. It does all the work for us. And then once it's ready to go, we can resolve symbols in the loaded payload, execute them, we are good to go. So 20 lines of code, thanks to Apple APIs, in-memory code execution was trivial. And this was all well and good. This is what all the implants and the public malware was using, until we noticed that in dyld version 3, Apple stealthily, or without any fanfare, actually modified their APIs to actually always now write out the memory buffer or bundle to disk. So if you would download it into memory and then call these APIs, behind the scenes, they would actually write it out to disk and then load it normally. And we'll see this template for the file path. We saw this mentioned in several of the previous talks as a detection vector. So this was rather unfortunate because this essentially meant that in-memory code execution, or this reflective code loading, was undone. So now if we compile Apple's memory-based bundle, and we try to execute a bundle that we've either downloaded in memory, we can see that it's actually written out to disk. It has now a file name that always ends or starts with NS create object file for memory, and then with 6 or 7 random letters. And then if we run a file monitor, we can see, yes, indeed, what is happening is it's actually being written out to this location. So Apple has basically just neutered or undone the in-memory code loading. And so this was kind of a bummer because we were like, this sucks. Well, I mean, not really, but we did have to evolve. So now let's talk about restoring in-memory loading on macOS 15. And we have a goal and some observations, and the goal is to restore the ability to directly execute compiled binaries directly from memory without having to write a whole loader ourselves. Loaders are insanely complicated. We don't want to do that. There's some observations. In-memory loading is still really supported. It's just Apple changed their APIs. And also, the loader runs in our own process, which definitely gives us some options and flexibility. So the first approach, and this is kind of just an interesting exercise, we will improve upon this, was just to use a RAM disk. And a RAM disk is a block of memory that the operating system would treat as if it was a file. So our plan is very simple. We first create a RAM disk. If we look at Apple's API, we notice that they look at the tempter environment variable, and then that's where they write out the in-memory payload to. So if we can set that to the RAM disk, in theory, the API will still write it out, but since a RAM disk is really just a memory block, it won't actually touch the file system. So it'll get written out to the RAM disk and then loaded and executed. So this is how we do this. We very simply create a RAM disk. We set tempter to this RAM disk. We execute the memory-based bundle code. And now we can see that even though the API writes it out, it's actually just copying it to a RAM disk, which doesn't exist on the file system. However, there's two problems with this approach, is that file events are still generated. So even though we're not writing out a file, a RAM disk is kind of like a file system. So an endpoint security monitor or a file monitor would still see those events. And if it was keying off that hard-coded file name, it would both be able to observe the fact that the payload was written to the RAM disk and also be able to go grab that, because the RAM disk is globally readable. So we're making progress, but room for improvement. All right, so what about that file name? That file name is hard-coded in Apple's APIs, and we saw talks earlier today that mentioned the fact that this is actually a really good IOC for any of the public malware samples or any malware sample that's trying to do in-memory loading. I don't think that the malware authors realize that their payloads are being written out to disk, and no one is using these APIs for legitimate code. So if you write a IOC that simply looks for that hard-coded file name, you will detect all sorts of weirdness going on. But here's the thing. That file name is built with the strlcat API. And what strlcat will do is simply copy up until some max size. The max size in this case is called max path or path max. So what we can do is we can just create a directory that already is of size path max. And then when that strlcat function is called to append the file name, it will be like, oh no, the buffer is already full, and then won't actually create that file name. So here we can see that if we set temp directory to our RAM disk that has a bunch of nested directory structures, if we execute that in-memory bundle, it will be written to that RAM disk, but that file name is now something we can control. So if there's any security tools that are looking for that specific hard-coded file name, they will no longer hit on that. So we basically thwarted perhaps these file and log monitors. So that's good, but again, there's room for improvement, and Adam did some neat research that basically patched the loader. I'm not going to go into this. He wrote a great blog. This could be a talk unto itself, but the idea is he could hook or patch some of the functions that the loader calls to prevent the fact that the file was being written out to disk. And you can see his code. It's rather involved. It's impressive, but it does suffer a little bit from the side effect that a file is still written out. He hooks the file writing so it's not his file, but still it's a little bit noisy, it's a little bit complex, and you do have to modify memory permissions. So again, let's recall our goal though. We're trying to restore the ability to execute compiled binaries directly from memory, again, without trying to write our own loader. And we don't want any files. The RAM disk thing was kind of neat, but too many artifacts, right? And so my question was like, can't we just use an older version of dyld? And spoiler, the answer is yes. So older versions of dyld exist. It's open source. So literally all we have to do is get an older version of dyld, compile it, and then invoke it. And this restores code memory execution on macOS. So here's some example code to do that. We have the required dyld files. We don't need the whole thing. We just need a subset. We can then compile them, and then I've written a function here called dl open from memory. We can see we now invoke the older dyld APIs and classes that don't write out the memory payload to disk, but still do all the logic of the loader, which we didn't want to re-implement, right? Memory alignments, imports, blah, 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 blah. So we can see that in about 17 lines of code. We call instantiate from memory. Again, that's an older dyld function. We call then link, which links the binary. And then finally, we execute the initializers. And I was like, no way this is going to work, but it does. And so once we have this dl open from memory function implemented, in 3 lines of code, we can download a remote payload from a server. And then we can pass it to this DL open from memory. This then passes it to the older dyld loader code that we've compiled directly into this loader, and it works perfectly. And if we run a file monitor to make sure no file events transpire, we can see that nothing hits the file system. Now you might think, okay, that's neat and good, but don't you need like some special entitlements? You're basically like executing unsigned code in macOS. And the answer to that is yes, if you're using the hardened runtime. But the reality is you don't actually have to use the hardened runtime. It's an opt-in capability of your binary. Now, if you do want to get it notarized, you will. So if we opt into the hardened runtime and then re-execute our code, which downloads a payload from memory and then goes to execute it using dyld's older code that we've compiled in, we can see that as soon as that code is about to be executed, the operating kills it. And this is because the hardened runtime requires that the code has to be signed. And in order to check that it's signed, what does it do? It looks for an on-disk binary to check the code signature to make sure it matches. If there's no binary there, it's like GTFO and kills you. Means you basically have to have something on disk. But wait, you don't actually have to, because it turns out there's some exceptions that the hardened runtime allows you to opt in. So what we can do here is we can simply opt into the hardened runtime, but add these Apple-supported exceptions. There's several we can opt into, unsigned executable code, or this other one. And if we add them to our loader, now even if the hardened runtime is enabled, we are still able to download and execute code from the internet directly from memory with basically no detectable attributes. So if you're a hacker, this is like insanely straightforward. You should create a simple loader using the older dyld code. Enable the hardened runtime if you want to get notarized. Perhaps you want to distribute your loader, modern versions of macOS. Submit it to Apple. Apple will notarize this. Notarization simply blocks malware. If you're submitting a simple loader, that's fine. You're not doing anything wrong. You can use private APIs. You can do whatever you want. Apple will still notarize this. Now, this does mean Apple has a copy of your loader, but if Apple ever figures out that it's being used maliciously, they don't have access to your payloads. They just have access to a simple loader, which doesn't really reveal anything. Okay, what about detections? It's important to talk about. So first off, I was like, okay, let's see if there are A, either any unified log messages, or B, any endpoint security events, for example, mmaps, something, because like we want to be able to detect the fact that in-memory code execution is occurring. And so I added a little like press key to continue into my proof of concept so that when you start the loader, those events are just normal. We don't care about those. But it turns out there are 0 log messages and 0 endpoint security events. I use the very excellent Red Canary Mac Monitor tool written by Brandon here, which allows us to filter on a custom process, but otherwise say, give me any and all events, and we can see 0 events are generated. This was surprising. I thought, for example, at least some nmap events were, but turns out it's not the case. Now, there are some reactive things we can do because executing a binary directly from memory is a little anomalous. And so the first thing we do is if we view memory mappings of a remote process that has one of these payloads executing, there will be some strange things. The problem is we can't directly do that, so we have to defer to an Apple command line utility, specifically vmmap, which has the appropriate entitlements to read memory mappings. It doesn't tell us the contents, but it will show us that something is strange in memory. And it's interesting because it maps it as dylib. That's vmap basically saying, hey, this is a binary that doesn't have an on-disk component backing it. And so you could, in theory, if you ran vmap against every process and one of those processes happened to be doing in-memory code execution, you would see this strange mapping. So again, it's kind of reactive and might be useful. Another idea is, well, what if that in-memory module is doing something? There should be remote threads. Well, again, because of Apple's decision, we as security tools can't enumerate the remote threads of remote processes, but a tool like Sample can. Problem is Sample suspends the process. And again, this is also a reactive approach. So you would have to run like Sample against all processes and hope that if there was in-memory code execution, it would be spawning a thread, et cetera, et cetera. But if it was the case, we would see in the stack backtrace of the executing threads there would be an entry for unknown binary, which would indicate that this binary is in memory only. There's no corresponding file on the file system. And what about flagging those exceptions? If you decide to opt into the hardened runtime, which probably you would only do if you wanted to get this loader notarized, I thought, okay, maybe like that would be a red flag. So I wrote a little script, actually ChatGPT did, and that went through all the applications on my system to print out any that had these exception entitlements. There was over 60 apps in my computer that were opted into the hardened runtime, which is good, most apps should, but B, had these exception entitlements. So that's kind of unfortunate because it means we can't really use this as a detection mechanism because there will be a high number of false positives. So, pardon my French, but the shitty thing is, really the only thing we can do is basically ignore the loading and instead try to focus on detecting the activities of the in-memory modules. Because the attacker is probably going to do something observable once their code is loaded and executed. They might try to access the keychain. They might try to do other things. And Coulson, who spoke earlier, has a great quote that basically says, it's wise to focus on rather the behaviors or the payloads. But even if we can detect that something funky is going on, we cannot access those in-memory payloads. There is nothing we can do. As defenders, we are screwed. So, conclusions and takeaway. In-memory reflective loading on macOS is alive and well. Don't use the Apple APIs, which are now neutered and will stealthily write out your payload to disk that security tools are all waiting to capture and will. And I showed you it's super simple. Just compile in the older versions of dyld that support in-memory code execution and implement all the loader logic yourself. You don't want to write your own loader. And if you're a hacker, like, why are you not using in-memory code modules for everything? Because I showed there's really nothing, or basically nothing we can do as defenders. We can, yes, maybe detect that a process is doing this, but because of Apple's failure to strike an adequate balance between security and privacy, we are just left in such a conundrum. And this is just yet another example where ultimately the attackers are empowered by Apple's privacy decisions. I don't have the answer to this. Maybe one answer is Apple could have an entitlement that allowed notarized security tools to scan and remote process memory. But I also understand there are some privacy concerns there. So Apple, yes, is kind of between a rock and a hard place. But in the meantime, the attackers are super, super stoked. All right, I'm done. Don't shoot me. So again, I just want to thank the supporters for helping support this amazing research. Also, there's a lot of, as I mentioned, especially previous research on this that really goes more into the topic of this reflective code loading. Again, it's all specific or previous to macOS 15. The novelty of this was the evolution of these techniques for us to restore in-memory code execution on macOS 15 and show that, unfortunately, it's essentially completely undetectable. So that is a wrap.